Good evening and welcome to the Scientific Adventures of Beardman. Today we're going to be looking at some of the properties of waves. First thing I want to do is go through waves and talk about some of the different parts, give them names so we can talk about them by name. And that will help us as we begin to gain an understanding. So to begin with, I did a little adjustment on my beard here, and you can see we've got kind of a transverse wave. You have to imagine it kind of carrying on there. Okay, so this point here would be the highest point where the wave is most displaced from equilibrium above the equilibrium position. That would be known as the crest. Okay, and the lowest place, imagining at this point it comes back up, the lowest point, this is called the trough. Okay, equilibrium would be kind of halfway in between, and this is temporarily up here. In a moment this would drop down and I guess go kind of like that. Okay, anyways, so we have the crest and the trough. Now with a longitudinal wave, that's a little bit hard to do. Let's see if I can get my beard to do that. We have a compression, okay, which is where the particles have moved together, and then a part where it's kind of more spread out, which would be called the rarefaction. Now that's the word that's probably brand new for you, rarefaction. And then we'd have another compression a little bit farther along. And then as that traveled along, we'd get the rarefaction here and the compression over here. All right, that got a little weird. Anyways, so those are some of the key points that we're going to want to be talking about. Another one is the amplitude. Okay, amplitude is the maximum displacement of a medium from rest position. So if our rest position was right here in the middle, this distance here would be the amplitude. Perhaps we should draw a picture. The beard's getting a little weird. So you can see here in this transverse wave that as it's going up and down here, we've got the distance from rest position to the top as the amplitude. Notice if you were like surfing this wave, now keep in mind this is not a surface wave, this is a body wave. But let's just pretend for a moment that it is a surface wave. If you were surfing this, you're not talking about the height of the wave, like the face of the wave. You're talking about the amplitude, the displacement from rest position, not the distance from crest to trough. And that's the amplitude. One thing to know about the amplitude is closely related to the energy. Okay, because the more energy that wave is carrying, the higher it can lift the material, or the lower it can push it below rest position, and that takes more energy, and so it's carrying more energy as it's moving along. Another thing that we might be concerned with is wave speed. Okay, how fast is this wave traveling? Okay, the primary thing that affects wave speed is the medium it's traveling through. Okay, so if we want to increase wave speed, basically we increase the connection between the molecules, and the more connected those molecules are, the faster the wave will travel. Okay, to calculate it, it is a speed, so you can calculate it as just the distance the wave travels divided by the amount of time it takes to get there. Okay, that's our oldest equation in this class. Velocity equals displacement divided by time. But there are some ways you can get to that without seeing that as easily. Waves aren't always easy to see how fast they're traveling depending on what type of wave it is. And so there's a way to break that down a little bit. If we take a look at two terms that deal with a wave, we can find an easier way to calculate that, or another way. Sometimes distance divided by time is the easiest. One of those things is wavelength. A wavelength is the distance from the distance between a point on a wave and the same point on the next cycle of the wave. So the same point would be a point that is displaced from medium the same amount and has the same slope. Okay, so you often do it from crest to crest because crests are easy to see. Okay, could be from trough to trough, or if it's a longitudinal wave, from compression to compression, or from rarefaction to rarefaction. But you could really pick any point on the wave. Point right here, this far above, slope is down. Okay, and we go until oh, here's the same point, but slope is up. That's not the same place. We have to go until the slope is on its way back down, the same displacement. Okay? And so that distance is a wavelength, and that's measured in meters. You can see that could end up being like our distance. Okay? Well, another term is period. A period is the time required for one complete cycle of a periodic motion. Okay, so while that applies to things like pendulums and things vibrating, it also applies to waves. Okay, so a wave is a periodic motion which repeats itself. So if we watch that wave until it repeats itself again, then we would have a period. Okay, well, if the wavelength is from one point until that point repeats itself, the period is the amount of time then until that wave gets to that next point. So really we have a distance and we can divide by the time. We just have different symbols. Wavelength, we use this symbol lambda, okay, measured in meters, but the symbol for it is lambda. And period is a capital T, separating it from just any old time, saying this is a special time. This is the time that it takes to complete one cycle of a periodic motion. Okay, so we can do velocity equals distance divided by time, and a special distance is the wavelength, and a special time is the period. Now, there's one more step. Sometimes it's not as easy to figure out the period, seeing how long it takes to complete one cycle. Sometimes it's a lot easier to do the inverse of that, which is to count how many cycles go by each second. This is a value known as the frequency. Frequency is the number of complete cycles per unit time for a periodic motion. Okay, we'll be using per second. Okay, and instead of writing frequency equals 60 per second with no unit in the numerator, we have a special name for that, and we call it hertz. So 60 hertz means 60 cycles per second. And usually we don't write cycles, but 60 of them are happening per second. So now, if frequency is just the inverse of the period, because if a wave takes 2 seconds to go by, then half a wave is going by each second. Or if a wave takes half a second to go by, then 2 of them are going by each second. So they're just inverses of each other. Well, if they're inverses and lambda divided by the period gives us the speed, well then if we just inverse the period, we get lambda times the frequency equals the velocity. Okay, and so that's going to be the main equation that we're using. Okay, keep in mind velocity will be measured in meters per second, wavelength, lambda, will be measured in meters, and frequency will be measured in hertz, but don't forget you can just substitute for that per second. All right, have a fun time enjoying your waves. Oh, one other thing. As we talk about waves traveling through a medium, one thing to note is that if you have a longitudinal wave, that kind of wave can travel through any type of medium because it just involves one molecule bumping into the next one. But if we have a transverse wave, okay, that wave requires that this molecule is connected to the one next to it. If we were in like a liquid or a gas and this molecule went up, this one wouldn't go anywhere because it's not connected to it. It's only when we're in a solid that these are bonded together, and when one goes up it pulls the next one with it, that you can get a transverse wave. Okay? That can only happen in a solid. So if you ever have a liquid, the only thing that can go through that, or a gas, the only thing that can go through that is a longitudinal wave. Thanks for watching us here on Scientific Adventures of Beardman. I hope you have a great day. Bye-bye.